So for this example, we're going to look at two different polynomials, x to the 9th and x to the 6th, and we are asked to find all inflection points if there are any. We'll also look at the graphs to kind of see visually what is going on with the inflection points, or if there aren't any. So we'll start with f of x, and whenever we're asked about concavity or inflection points, we should recognize that what we're looking at is f double prime. So I'm going to write down the global process for finding inflection points. So to find, if the directions are talking about concavity, like where are you concave up or concave down, so intervals of concavity, and or inflection points. So in order to do that, the process is we need to find, it's a similar process for our local extrema, in the sense that we're doing similar algebra, but we're looking at f double prime instead of f prime. So we want to find all places where f double prime of x equals 0 or f double prime of x does not exist. And the second one is because there could be a break in the graph where we change from concave down to concave up that we don't get from here, but we do get from here to find all of our intervals of concavity. It's not going to give us an inflection point if it's a break in the graph, but it will give us where are we concave up and concave down. And then we look at either side of these places. Look at either side of these places where the f double prime either doesn't exist or equals 0. What do I mean by look at? I mean that we look at is f double prime positive or negative. And so we can play like a number line game like that. So we'll see this in these examples. So for the first one, we want to look at the second derivative. So I'm going to do it a little bit quicker than I would otherwise, being careful. 9x to the 8 is the first derivative, and 72x to the 7th is the second derivative. And this is always defined. There's no problems with division by 0 or 0 in the denominator, in other words, or negatives underneath the square root or other places. This makes sense for any x. And so the only place we could possibly change sign where this could change from positive to negative or vice versa is by going through 0. So x equals 0 is the spot. Look on either side of these places we want to do. So, whoops. If we look on either side of 0, pick your favorite negative number, and we plug it in, and because it's x to the 7th, 72x to the 7th, it stays negative. And so that tells us f is concave down, which I'll just shorten that way, if we were asking about concavity. If we plug in our favorite positive number, f double prime is positive, and so we're concave up. Now this becomes an inflection point because we change from concave down to concave up, and it's a point on the original graph. So we have an inflection point is at when x equals 0 and it ends up being the origin. And when we see this, when we first look at the graph, we see that it might not be obvious that's exactly where it changes concavity from looking at the graph, but calculus helps us find that. For the next example, we're looking at x to the 6th. So we play a similar game, if you will. We look at the second derivative, and we get g double prime is 30x to the fourth. And so, similarly, we only need to look at, I'm not writing everything down, we only need to look on either side of 0. Because that's the only place, x equals 0 is the only place this is going to possibly change sign. And here we notice that g double prime, because it's an even power, is always positive. So in this case, we're always concave up. And what happens with this one is, if we look at the graph, we can see that we didn't look at critical points, local max or min, but we'll see there's a min there, and we do not change concavity there. Just for a brief second, right at that instant, we have absolutely no concavity. Is one way of looking at that.